This lesson is for Chapter 2, Section 6, Arithmetic Combinations of Functions. So if everybody would please get out their notebook, be ready to write down your examples, and turn in your textbook to page 214, we will get started. So combining functions. It is exactly what you think it's going to be. Adding them, subtracting them, multiplying, or dividing them. If you're going to add two functions, you do exactly that. You take them and you add them together, combining like terms. Subtracting, same difference. Multiplying two functions, f times g of x, you just take f of x times g of x. Watch for this because most of our functions involve more than one piece, so you will be distributing, foiling, etc., when you multiply those two functions together, so watch for that. Quotients, dividing with functions, that is also something that works. F divided by g of x is function f of x divided by the function g of x. So the next few examples, I pulled the checkpoint problems for example 1, 2, 3, and 4. So you can look in the textbook at those examples that are done for you. And I chose the checkpoint one so that we could have a few more to look at together. So if we have f of x equals x squared and g of x equals 1 minus x, find f plus g of x. So that's going to simply mean we're going to take f of x and we're going to add it to g of x. So if f of x is x squared and g of x is 1 minus x, adding those two together, we get x squared minus x plus 1. Now, this asks us then to evaluate it also when x is equal to 2. So if we're going to do that, just plug 2 in for all of the x's that you see. Oops, minus 2. So 4 minus 2 plus 1 is 3. Finding f minus g of x. Same exact functions as the problem before. But if we take f of x minus g of x, then we will have x squared minus 1 minus x. Okay, now here's what I was talking about before. Careful when you subtract. You're subtracting all of g of x. So just like when we were subtracting our polynomials earlier in this course, remember that you're subtracting each item. So subtract 1 and subtract a negative x. So then we end up getting this as our function. Okay, now we're supposed to evaluate this one for x is equal to 3. So put in the 3. So 9 plus 3 minus 1 is 11. All right, so now same functions we're sticking with again, the checkpoint does. We're going to do f times g of x, and then we are going to evaluate when x is equal to 3 again. So if we have f of x times g of x, x squared times 1 minus x, okay, see that this is going to be a distribution. We have x squared times 1, and then minus x squared times x, and we get this. If we evaluate this for x is equal to 3, we then get 3 squared minus 3 cubed, which is 9 minus 27, or negative 18. then a quotient 1, f over g of x, and we're also going to compute g over f of x for the two functions. F of x is the square root of x minus 3, and g of x is the square root of 16 minus x squared. Then we are asked to find the domains of f over g and also g over f. All right, so kind of a lot with this one. Let's see how we do here. The first part, basically very simple. F over g of x is f of x over g of x. So we have square root of x minus 3 all over square root of 16 minus x squared. Okay. Then, likewise, we do the other one. So now we have square root of 16 minus x squared all over square root of x minus 3. Okay, so those are the two functions that we come up with when we divide these functions. Now we are asked to find our domains. Now, domain of f of x. Okay, if we're looking at strictly square root of x minus 3, remember that we cannot let that value underneath our radical sign end up being negative, but it can go positive for forever. All right, so what's the lowest x value that we can put in there that will still work? Well, x could be 3. That would give us the square root of 0, which is 0. It can't go under that, though, or we're going to have a negative square root. So the domain of f of x starts at 3. And goes to infinity. Okay? Now, let's do g of x. Again, we need to make sure that we don't end up with a negative underneath that square root sign. Now, the most that you can subtract from 16 and stay 0 or higher is going to be a positive 4 or a negative 4, correct? Because that would result in 16 minus 16. If we would go with anything over 4, we're going to be taking 16 minus something larger than itself. We get a negative amount. We can't. So we can use a 4. We can use a negative 4. Or anything in between them. Okay, so anywhere from negative 4 itself all the way up through 4. Now, when we're looking for a domain of these two together, we're looking for their intersection. Okay, so if we intersect, we look for where they overlap. Because then those are things that can be used and satisfy both of them. Okay, if it only works for one of them, it's going to end up making the other part either undefined or imaginary or something, and so we can't use that number. So we're looking for what is in both of these. Well, both of them have 3, okay? But if we were to put 3 in f of x for the quotient where it's g over f, that would make a 0 on the bottom, and that's undefined. So the 3 itself sort of kind of works. It works for one of them, but not if it ends up in the denominator. So we give it a curved parenthesis 3. Now we can go with the other one all the way up through, oh, excuse me, we got to do 2 intersections here. I need the domain of this first one here. Sorry, domain. So where do these two intersect? All right, so in this one we can use the 3. That would just make the top 0, and that's all right. We can go all the way up through -4, or up through +4, but not on the 4 itself, because that would make the square root of 16 minus 4 squared 0. Okay, so 3 ends up in both of these, and not quite 4 can work with both of these. All right, so the domain of f over g of x is going to be from 3 up to just shy of 4. Okay, so not a very huge domain there at all. Let's do the same thing for the other function. Okay, now when you're looking at this one, again, we have to make sure that the bottom doesn't become undefined. So we're not going to be able to use the 3 itself. But anything just over it works just fine. And the 0 on the top is going to hit when 4 is put in, or -4, but -4 doesn't work in the bottom, so we're not even considering it. And we can let the top be 0. We just can't let the bottom be 0. So we've got a curved parenthesis on 3 this time, and a bracketed parenthesis at 4. All right, next thing, composition of functions. A composition of function is when one function is put in for x in another function. So shown, the notation that they use is kind of this open circle or open dot, f composed of g of x, and it just means that in your function f of x, the g of x function is going to be inserted for the x's that you have in your f of x function. Okay? We are also going to be asked to find domains of this kind of a situation. The domain of f composed of g is all numbers in the domain of g, so that g of x is in the domain of f. Okay, so the domain of g is, so g of x is in the domain of x. All right, we'll take a look at an example of that. All right, everybody on the bottom, page 216. That's where this checkpoint problem is coming from. If given f of x is equal to 2x plus 5, and g of x is 4x squared plus 1, find the following. So f composed of g means we take our f of x function, and in the place of the x, we are going to place our g of x function. Okay, so instead of having 4x squared plus 1, as g of x, our f, well, I'll write it like this first. Now you can see why this is going to go in there. Maybe a little bit better. Okay, which means then for every x in our f of x function, we're going to be putting 4x squared plus 1 in. Okay, so this was the original f of x, was simply the g of x inserted for the x feature of f of x. Okay, so hopefully that makes sense. And now we just start to simplify. Distribute your 2. And simplify. Okay, so f composed of g of x is going to be 8x squared plus 7. So let's do this one. Similar thought, but now we're going to take the f of x function and put it in for all of the x's in the g of x function. So 4, and the 2x plus 5 is squared, plus the 1. Now remember, 2x plus 5 squared is a 2x plus 5 times a 2x plus 5. You have to FOIL that. which would give us this. Then distribute your 4 through there. And combine like terms. And there's that one. Now the letter C checkpoint asks us to evaluate f composed of g at x of negative 1/2. So go back up to f composed of g. That one we got 8x squared plus 7 for, remember that one? Okay, so now insert the given x value. Negative 1/2 times itself. Negative 1/2 times negative 1/2 is 1/4. Eight times 1/4 is 2. Which gives us an end result of 9. All right, then we move on to the domain, again, of a composite function. Remember a couple of slides ago that the domain of f composed of g is all the numbers in the domain of g, so that g of x is in the domain of f. Okay, so let's take a look. Find the domain of f composed of g of x for the functions f of x is root x and g of x is x squared plus 4. All right, so first let's do our composition. If we've got f of g of x, that's going to be the square root of x squared plus 4. Okay, insert g of x for the x in the function f of x. Okay, when you're looking at this one, let's pick apart our two domains. Domain of f of x. If it's the square root of x, remember we can't allow that to be negative, but that would allow us to have anything from 0 to infinity in that domain, right? Okay, let's check out the domain of g of x. Okay, g of x is x squared plus 4. Okay, now with x squared plus 4, there are no values to put in there for x that are going to make that function undefined. So we're going to get all real numbers. So everything from negative infinity up to positive infinity work in that function. Okay, so now if we're looking for this domain for our composite, we're looking for their intersection. Another word that you could use to replace intersection with, if that one bothers you, look for your overlap. Just like two streets that intersect, their intersection is where they overlap each other. The intersection of two sets is where the two sets overlap each other. All right, so both of these sets have 0 in them. And they both go up to infinity. So here is your intersection or your domain of these two composites. Now, decomposing a composite function. This is the reverse of putting two together. All right, we've been doing the composites here for a couple of slides. Now we're going to decompose or take them back apart. So let's see if we can't wrap our heads around this one. We're going to decompose the function h of x, which we've got the cube root of 8 minus x over 5, and we're going to write it as a composition of two functions. Okay, grab the innermost function. Make that g of x. So that innermost function I see is an 8 minus x. Okay, let your f of x be everything else. So the cubed root of something over 5. Okay, so then in essence, if you look at what we started with, it could have been stated in terms of f of g of x then. Okay, so if f of x was a cube root of x over 5 and g of x was equal to 8 minus x, that would have given us that thing that they started us with. Okay, and that's all there is with that part. All right, so there are a couple of application problems. If you turn to page 218, I think when you're looking through this one, example number 8 at the top of page 218, it's not bad at all. Give it a look. There aren't too many application problems in this section, so I decided not to make a slide for it. I figured you could look through the one that's in the textbook. The checkpoint one is very similar to it. So in your assignment, then starting on page 219, please focus on 1 through 46. Okay, but the 47 through 54, flip there real quick. Those are the decomposing a function one. Play around with some of those odds and see if you can pick it apart like we did that last example that was done together in the video. And then after that, starting with number 55, there are a few application problems. Give a couple a try. At least give the odd ones a try where you can look up and see if you got them all. As I'm looking through them and noticing them, they have many parts with them, like A, B, C. Some even have A, B, C, and D, and E parts. And there are a number of you, when you do application problems, you skip some of those answers. So give yourself a little practice on a few of those that have the multiple steps. All right, I think that's all I've got for you. So come back to class tomorrow with questions if you have any.